Welcome back to the channel. Hope everybody's doing well, and in today's video we're going on to part 2 of looking at testing out one of these little temperature pucks that I've got from Amazon, this one here. In the previous video I tested it purely against the U1461A, measuring the output and using the 1041 resistance box here as the simulating the temperature input. I'm going to continue using the 1041 to provide the input in this test, and what I've done is set up all the other little process calibrators that I have available to me to measure the voltage output as well and see what the accuracy comparison is using these units against what my existing setup is, henceforth why I'm keeping the 1041 as the simulation aspect at this moment in time. Now what I did do in the previous video is I tested this and measured it against the nominal output from the temperature puck, which is slightly wrong because I don't know how accurate this temperature puck is. So what I've done is tested this against my DMM7510, and I'll put the results up for that in comparison to the measurements I made on the U1461A. So you can see here the temperature puck is 0.274% accuracy, average accuracy over all the measurements when using the DMM7510, which is slightly out of tolerance. It's got a maximum of 0.2%. In terms of this U1461A against V out, this is 0.378% accuracy. However, if I compare the measurements from the U1461A here to the DMM7510, this accuracy comes down to 0.121%. So that's what I'm going to compare all these instruments to, the average accuracy of 0.121%, to see if they offer any improved accuracy. Now I'm not going to go through all the measurements on this. If you want to see the measurement points being done, you can go back to the video on this U1461A here. I'm just going to put out a few salient points as we go through. You can see here we are on 80.11 ohms, which is equivalent to minus 50 degrees C, and we should be getting 0 volts output. And you can see we've got some good correlation here, haven't we? Our U1461A is 0.011, 0.011 on our HT8051, again on our Uni-T there. If we take a look over here, again continuing 0.012, so it's down here, isn't it, on this one? On the Finersi it's up at the top, 0.0, that one's oscillating a little bit, and it's the only one that is down to our LB02 here, 0.011 again, and 0.01 on our SG-003A. This is the only one currently displaying just 2 digits. Everything else is all to 3 digits. So what we'll just do is wind this up to equivalent of 6 volts output. 8.34, so that should now be 6 volts coming out, and this is the one that's out the most, or closest to being out the most. There's our 138.34 on the 1041 there, and we've got 6.208, again fairly good correlation across all the values, 6.027. Again, our Finersi is bouncing around, but 6.03 on the SG-003A because of the lack of a digit. But all the others, 6.205 to 6.029, we've just seen on the Finersi. So fairly good in that respect. I'm just going to take it up to 7 volts, which would be 147.78. So immediately we see now our U1461A has dropped to 7.02, it's lost a digit, so it's the same as our SG-003A there. All the other devices have retained their 3 decimal places, and we're 7.0265, so 7.0256 on the Finersi there. Perhaps not, it's perhaps a little bit more stable, but it does still rattle around a lot more. Let's just zoom in a little bit, so if we can just show you that a little bit more. So yeah, that's a really bad display on the MR9270S there. It's the lights that's affecting that, unfortunately. So there you can see it's still bouncing around a little bit on the Uni-T. So let's just zoom out again. And our final one is obviously 10 volts, which is 175. 64634, so that should be 10 volts, and you see we've pulled our accuracy back much closer value, 10.01 on the U1461A, 10.009, Uni-T 10.011, Uni-T is even closer, 10.0078 there. And then the other two down at the bottom there, 10.01 and 10.02/1 on the SG-003A. So we'll put some results up for the instruments. We've got this comparison plot here. This is done in 3 blocks. So on our left hand side there, we've got the average tolerance of the measurements. In the next set of blocks, we've got the tolerance spread. And at the end there, we've got the cost of each of these setups. So if you look at the average tolerance, the best 2 instruments in the middle there, they are actually the SG-003A and the LB02. We do have to be a little bit careful with the SG-003A because with it having 1 digit less of resolution, sometimes it gives the impression that it's more accurate because you haven't got that 3rd decimal point taking the value away a little bit further from the nominal or the actual value that you're seeing. But then you see 0.06% for the MR9270S is the next best one. 0.15% for the UT705 is actually the least accurate of all the instruments. But having said that, all the instruments are within that 0.2% tolerance value of the measurements taken on the DMM7510. So overall it's a good result. They're all within the specification. It's just that you've got a little bit better performance from a couple of the instruments there, probably 3 of the instruments. The LB02 and the MR9270S would be the ones that I would look at there personally. So we'll move over to the second block of results there, the tolerance spread. Interesting to see this because your SG-003A, that has one of the most accurate average tolerances, has one of the worst spreads. Not quite sure how it's managed that, but that's what the maths has come out as. The better instruments here, we've got 0.16% for the HT8051, that's got the least spread, that shows the best stability, and the LB02 at 0.17% is very close to our HT8051, as is really our MR9270S, 0.19%. Not much in it there really, as the other values there are up in the top ranges, aren't they? So nothing to shout about with those ones really. And then we'll move on to the equivalent cost. So this is the cost of the instrument plus the 1041 decade box. And our UT1461A is our most expensive item. So what I've done is effectively given that a 100% value. So the most expensive setup after that is with the HT8051. And I guess we get fairly reasonable results from that, don't we? 0.07% average accuracy and 0.16% spread. So it costs a lot, but you are getting much better results in comparison to the U1461A there. And then our cheapest option is the SG-003A, but we have a very high spread with that one. Next after that, 38% of the cost of the U1461A, we've got the LB02, and we do get very respectable results from that. 0.1% spread, 0.02% average tolerance is the best tolerance out there, so that's acceptable for this. The downside to that, of course, is that it has a little bit limited functionality in comparison to some of the instruments, and in particular if we look at the SG-004A and the MR9270S, that MR9270S there, pretty good on the average tolerance, pretty good on the tolerance spread, and at 43% of the cost of the U1461A%, I think that's probably the one that I would plummet to for this job really. Whilst the SG-004A does give fairly respectable results, you have seen on there that it does bounce around a lot. It lacks that stability there, which I wish Finersi would address in a firmware upgrade, although I doubt they ever will, but you never know. But in comparison, the MR9270S, they're much more stable. So that would be the instrument of choice for me for this. So as I said, this is part 2. I'm going to move on to a part 3 on this, and I'm going to replace the 1041 with some of those process calibrators there that can output a temperature and see how that affects. And obviously we have an accuracy issue there that we could be affecting, and also the time it takes to do the tests. So that'll be in an up and coming video. That'll be it for this one. Thanks for watching. Hope you found it interesting, and I'll see you again in the next one.